Hi everybody, so I'm Filippo, I'm the R&D leader at MX3D, and I'm going to show you today our latest project within the Integradde fund, and concerning the world of infrastructure. So a brief introduction about MX3D and what we do. So we are a WAAM solution company. We work a lot in R&D, as well providing a turnkey WAAM solution, software solution and control system. We also have one of the nicest WAAM workshop floor in the world, I would say, and therefore we do a lot of on-demand services. What are we going to see in this presentation? So why is WAAM for infrastructure relevant? Who is needed in order to make WAAM for infrastructure real? Material research and qualification. So we are going to see some more hands-on consideration about what my colleagues has discussed before. Design optimization, system integration, and how to print a demonstrator. So what is WAAM? First of all, it has been discussed before, but we're going to see it again. Here you see one of our machines. So it's in the most classic configuration. It's a standard welding robot connected to a power source or welding machine. In some case, a manipulator, as you see here. So it increased the amount of axis. And a smart software capable of driving this hardware in an additive manner rather than the classic use of a welding robot. So how does it work? Well, basically it's welding with motion and a growth in height, and the welds are deposited one on top of each other using specific parameters, perhaps slightly different than what commonly used for the standard welding application. So the key input are, well, of course, electricity, wire spool, so that's our feedstock, it's standard welding wire, and gas. What are the perks of this technology? Well, it has a very low cost, both in terms of investment to get the hardware. As I said, welding robots are quite well established in the industry market, so it's not hard to find them, and you can find secondhand, new, whatever, to a very reasonable price. And the maintenance costs are also very low. So since it's also based on welding, all the consumables and the feedstock are available on the market. They are not, unlike powder or so, particularly expensive because they're of generic use. The deposition rate is pretty high, depending on the application and the alloy, of course, but it can reach kilos per hour. As I said, availability of the feedstock, a lot of alloys, basically whatever is weldable can also be used for WAAM. There is a consolidated science around it, not necessarily around WAAM, but as it's pretty much of a green process still, but around welding, which is the main process behind WAAM, and it allows large-scale product, as we're going to see. So why is WAAM relevant for infrastructure? We did a couple of projects already to showcase this. It's a good perspective for the future of infrastructure industry because of the large scale, because of the material that can be treated. So we can go anywhere from carbon steel, high-strength steel, construction steel, duplex steels also for the more exotic. And it's very reconfigurable, so you can produce unique shapes or particular layout or topologies without having to reconfigure your machine. And it's, of course, suitable for optimized design, which are trending now in the world of infrastructure. Yeah, I will give some of the old example of what we did for an infrastructure world. So the MX3D bridge, some of you might have seen it already. It's been there for quite a while. It has been generated using the latest simulation analysis, generative design, so both a advanced engineering and also state-of-the-art design. It's long, around 12 meters, 6 tons heavy. It took a couple of months to be printed and way more years in order to be placed due to the lack of regulation. The optimized steel connector, this is project of a year ago, done in collaboration between MetalXL and Takenaka, a big Japanese construction firm. The scope here was to research certifiable and repeatable load-bearing joints of different layouts for civil engineering applications. So, talking about the exposed steel. Is in duplex due to the fact that it's an exposed structure, so it has to stand weathering. It's around 50 by 50 centimeters, 50 kilos. It has a hollow structure in the main branches, a solid core on the joining parts, and it has been filled with mortar for several reasons, saving costs on the steel, but also for the fire retardant properties. So we are now going to see the approach that we took in the Integradde project to the infrastructure world. At this stage, as you know, Integradde project is around halfway, and many aspects has been already consolidated. Some others are still being researched. So for the production of this first demonstrator, we have focused mainly on 4 aspects. So material validation through Imperial College, design optimization together with limit state, validation of the design. So this was done by MetalXL, limit state, and Imperial College all together. System software, that's where MetalXL got the biggest share, and building the part. Of course, all around there are a lot of other sciences that are now helping researching this approach and this process, and are going to be discussed later. But now I will just focus on the production of the demonstrator. So advanced product engineering, what does that mean? There is a big research behind. So it's not just about printing the final part, but it's also about validating all the steps required to print this final part. It goes from window of parameter research, printing specimen and testing them, as well as producing data by sensor network during printing that will also go and help the data provided by DT and NDT to have an even bigger picture of what's going on a WAAM part. In this case specifically, Imperial College has drafted guidelines for what kind of specimen we had to print, what was relevant for our end goal. In this case, we printed over 500 kilos of specimen for destructive testing, flat plates, but also T-joints and a bit more relevant parts, also beams and so on. We used two alloys, mild steel and high strength steel, to study the differences and how much of a difference these two materials will keep after undergoing the WAAM process. We have logged over 1 terabyte of data. This is going to help later on, and currently and later on, the simulation side of the process. And we have obtained 3 certifiable DPS. What does that mean? That means that we have now the position strategy. That's what the DPS is. That thanks to this route of testing and validation can now be considered of producing a stable output, which is very important for certification and repeatability. So the design optimization, as I said, it was done using limit state software, Peregrine, and we have focused here on trusses and joints. So under the guidance again of Imperial College and MetalXL, so Imperial College has provided use case as well as the material properties. MetalXL, we have provided information about the WAAM process, like what is the work envelope of the robot, what are the WAAM constraints. So Isabel showed before a bit of rules for additive manufacturing. These were general rules, but of course every machine system, every integration has specific rules, like the work envelope. It really depends on what robot you're using, for instance. The overhangs, they depend on how many axes you're using and so on. So we had to provide information about our specific system. Those information were used during the design process to create something that would already take everything into consideration, so we would not have surprises later on. So you can see that the work envelope, for instance, and the material properties, they were used at the beginning phase when Limited had to determine the design domain, the load, the boundary condition, and so on. Other rules like the WAAM constraint, so what overhang can you tackle, or other things like how sharp corners can you make, what is the smallest beam that you can print with a hollow section, were used to optimize and rationalize the geometry or generate the cross-sectional beams and the joints. So out of this, we got 3 different trusses, simply supported, cantilever, and 2 cantilever trusses, sorry. All the trusses encompass the similar construction. So we have circular members of different diameter, depending on their position within the layout of the truss. Connectors, very different between each other, but they all just need to connect the different beams. So where you can see the full truss, and in the detail on the bottom left, some details on these connectors. So you can see that they can be simple as connecting 2 beams together, but they can go as complex as connecting 8 beams together. On our side, we provided the right hardware integration. So we created a robotic WAAM cell. This is also a turnkey solution. It has everything already integrated, all the hardware, all the software, control system, and so on. So it has 8 axes, and that was very important for this exercise through an external manipulator. Power source, fume extraction, user safety, and ready for certification. Those were of course, very important things. The software used is also provided by MetalXL. It's called MetalXL, and it's a powerful CAM that provides also tools for geometry analysis, toolpath planning, inverse kinematics, the export of AML file. This is for interoperability, and of course the machine code. So this is the tool that was used to also to provide the design rules in the previous phase. For monitoring, that is also very important because it's WAAM is, due to the nature of the welding process itself, is not one of these processes where you just look through a window and you can see what's going on due to the high amount of UV produced by the deposition process. So it's important to have a virtual window on what's going on, and this is done through monitoring everything happening through sensors on the deposition side, but also just acquiring feedback from all the systems that are connected together. So for instance, to name some, you can have current and voltage probes, temperature probes, and so on, and tracking the motion of the robot, for instance. Those information will be used live, but they can also be recorded and used later for evaluation purposes through digital twin science, which is also pretty hip right now. What is it used for? Well, it's a sort of passport for the part that you have printed. You can attach it to the real part so that a customer or a user can validate that everything was printed within the specifications that a customer might have provided. And it's also used for certification, of course. It's really important, and review the print quality overall of a part. So now we go in the funniest part, so printing a demonstrator. How does that happen? First of all, we analyze the CAD. So we started with the simple cantilever truss for no specific reason. And we did a little bit of an analysis on the geometry. So you can see, even though the geometry is quite different, so the beams, for instance, have all different diameters, most of them. The nodes have different scales. But you can see that you can identify 3 subsets of nodes. So connecting 4 on the side, connecting 4 in the center, connecting 3 on the top. And you can see a repetition of zones, right? The layout is kind of repeating itself, however, with variation in sizes. When this was individuated, we could also plan a global build sequence. So what zone was printed first? So of course we start from the base. You see those two cylindrical connectors, and then you can print the first zone, and in a similar manner the second one, third one, and fourth one, and so on. So this is the progress, the overall progress of a print. On a more local side, you can see that we had to split each zone in sub-parts and plan the motion accordingly to avoid collision mostly, but also to maintain the proper layer orientation, because this is something that we have studied in the phase of mechanical testing. We tested parts to see also how the layer direction affects the mechanical properties. So we had rules also on that side during the build sequence planning. So here you can see on an even more atomic side what is toolpath planning for a complex part like this. And you can see on the image on the left, you see the split in zones of and areas of on this just this snippet of the whole truss. And on the right side, you can see the layer direction. Why are the layers planned this way? Well, on the members, so on the beams themselves, we try to keep the layer direction as more in line as possible with the flow of the beam. However, in the notes we had some rules, for instance, deriving from the tool clearance, right? We had to grant accessibility to the deposit, the welding torch. We had to minimize the overhangs, indeed, so try and maintain everything as vertical as possible, and avoid collision. So we did some validation prints, of course. We did not start just right away, but we wanted to test our build-up strategy. So here you can see this was a validation print on one of the single joint, exactly the geometry that you've seen before. And you can see on the right side the layer flow that is just as it was planned before. And the same we did on one full zone, also to see that the more global build strategy was valid, and there were no collision and there was no on, so the simulation were correct. After that, we printed the substrate, the first part, so the two big cylindrical joints that you've seen at the base of the beam. And we have printed them on a L profile that was also reinforced on the back, because printing already these two cylinders, it's well, there is quite a lot of heat going on, so they were massive solid prints. And to prevent warping, we use profile with extra reinforcement. And this profile and extra reinforcement are also useful for later when printing the entire truss to avoid warping and distortions of the substrate, which would then invalidate the entire print. So here you can see the print sequence of the zones and the full truss being printed. So you can see the base, the substrate was then reoriented in a vertical position, and the truss printed on top of it. So alternating, of course, substrate reorientation and layer deposition in following the toolpath planning that you saw before. So all in all, it was around 80 kilos of steel, most of which at the base. The two-cylinder, most likely, they were as heavy as the rest of the truss. The truss is hollow, of course. We used the mild steel alloy because also it's a bit more common in the infrastructure environment. So we decided to use that material. Is 8-axis printing, around 120 hours. Of course, this was a prototype, so we took all the time that we needed to make sure that everything would go right, and also to do some considerations in between. So it was, of course, not a print optimized for efficiency. Interpass temperature was a key feature, of course, of this print. Data logging and overall process supervision, that's simply meaning somebody going in and having looked that everything was going as planned. So a few more snapshots of the truss printing phase. So you can see on the left side one zone being printed with two different substrate orientation to maintain the layer direction as upright, as more following the beam direction, and also minimize the overhang. And on the right side, almost towards the end, we started printing the those little features that you have on the side for bolting. So this is the full finished truss in the cell, and well, it barely fit, as you can see. And some more screenshots of the truss. So on the left, as it came out of the machine, at the center it is sandblasted lightly, and on the right some detail on the of one interesting part of its layout. So the truss is around 2 meters high, just to give you a scale. So what did we learn from this exercise, and what are our plans for the future in the Integradde project? So clearly we need to improve the deposit rate, but I think that, as I said, like a lot of controls here were done and checks mostly to assure that everything was correct. You don't want to damage your hardware, and you don't want to have to restart printing a truss after you are already, for instance, 1 meter high. So we took it extra carefully. I think we want to reach a goal about of around 2.5 kilos per hour, which is very well in range with this technology's possibilities. Improve some alignment. We want to do a better recalibration, because we had a couple of times where we had to realign a few parts. So as you've seen, there are a lot of reorientation, a lot of change of base plane orientation, and if your hardware is not perfectly calibrated, then it can lead to misalignments. Contact tip to workpiece distance monitoring. So that's something that we're implementing now for inline correction. This is also part of the rest of the Integradde research, so we will rely also on the help of our partners to improve this science, but it's done through the use of probe and reading the welding curves. Log file stitching. So what we did now is we had to log each sub-print separately. So all the patches that you've seen before, they were almost one small print each, of course, all chained together, but the log files were still generated batch per batch, also to create smaller log files, because we're talking about terabytes of data for a print like this. So we want to have a system that automatically stitches those files together, and then it represents the full digital twin of the truss, rather than having to import many files at a time and patch them together. And keep improving the MetalXL suite. So from the software to the hardware, works towards making it more reliable and more sophisticated. So, for instance, we're now acquiring certification for the M1 cell and to our personnel, which is also very important if you want to acquire certified prints, and at the same time certify the DPS strategy, which is also very important. And we will unleash the full Integradde method. So as I showed before, for this exercise, we focus mostly on 4 parts. So feedstock material, the CAM hardware and the software, building the parts and the design. But there is way more that is going on at the same time. So we are building a process model, a multiphysics model, together with DSI, for instance, using the data derived from printing all the specimens that you've seen before for further simulation, as well as building AI supports to this methodology, to this printing technique. Interoperability, of course, is very important, because as you've seen already from the design to printing, there are quite a lot of steps where files has to be handled, and even more if you take into consideration process modeling, post-processing, and metrology. And indeed, acquiring certification, which is one of the goals. There is no reason to do all this if you cannot have a certified print, of course. So this was it, and thanks for your attention. And if you have questions, I think it's for the end of the whole webinar.
you.